Good morning everyone. This is Avinash Agrawal going to speak before you on the topic performance analysis of an IC engine. The performance of an IC engine depends on various factors like fuel air ratio, the speed of the engine, the amount of throttle opened, etc. Among these, the most important factor is the fuel air ratio. So now let us see how the performance of an engine varies with the change in fuel air ratio. The curve being shown in the figure is called Hooke curve or fuel consumption curve. In this graph, specific fuel consumption is plotted on the y-axis while percentage of maximum mean effective pressure is shown on the x. Fuel air ratio at constant speed and completely open throttle, you may see that 5 salient points from A to E have been marked on the curve. The point E represents an engine running with a very lean mixture whose ignition lag is so large that it causes an explosion in the intake system called backfiring. Now as we move from point E towards D by increasing the fuel air ratio, the specific fuel consumption improves or decreases. Beyond point D, if the fuel air ratio is increased, there would be no decrease in specific fuel consumption. Rather, it starts increasing from the point D. Therefore, the point D is a point of minima on the curve and hence it is called the most economic specific fuel consumption point. Now, the relative fuel air ratio at this point is 0.85. Now you must be wondering what is relative fuel air ratio. So, relative fuel air ratio is defined as the actual fuel air ratio to the chemically correct fuel air ratio. So, beyond point D, if you keep on increasing the fuel air ratio, the specific fuel consumption increases and the power produced by the engine also increases. Therefore, you increase the power produced by the engine only at the cost of economy and the price for running the engine increases. As we keep on increasing the fuel air ratio, point C is reached. Point C corresponds to the point where the relative fuel air ratio is equals to 1. Now, if the fuel air ratio is still made richer, the power produced by the engine will attain a maximum value at the point B, where the relative fuel air ratio is approximately equal to 1.1 or 1.2. Now, if you increase the fuel air ratio beyond this point, apart from the increasing specific fuel consumption, the power developed by the engine also decreases. This is due to the fact that the ignition lag produced in the engine is large, and so it may again cause backfire, as was the case with the lean mixture. As we know, taking into account the dissociation and the variable specific heat capacities, the maximum temperature in an engine is attained when the mixture is 20% richer. The indicated mean effective pressure is also maximum when the mixture is 20% richer. This also supports the fact that the graph drawn between fuel air ratio and the maximum temperature is same as the graph drawn between the fuel air ratio and the indicated mean effective pressure in an engine. Thus, through this discussion, we learned that the performance of an engine is most efficient when the relative fuel air ratio is 0.85. With this, I would like to sum up the discussion, and I would take this opportunity to thank Professor Rajkumar Singh sir, who encouraged me to do this video.